All right, Gen Chem Nation, we're looking at now temperature dependence, or the temperature dependent nature of our equilibrium constant. We've talked about this in the past, that in order to relate an equilibrium constant to a reaction, we must make sure that the temperature of the reaction is the same temperature at which that equilibrium constant is measured. So there's a relationship between our equilibrium constant and its value, its magnitude, with the temperature. How hot is it? How cold is it? Etc. And within this idea of thermodynamics, we now have two notions with delta G that invoke temperature as well as our equilibrium constant. For instance, what do we know at this point? Well, we know the delta G of an equilibrium process can be described by its equilibrium constant, or that delta G of a reaction, an equilibrium reaction, is equal to negative RT natural log of big K. We also know from the Gibbs free energy expression that our delta G of reaction is also equal to delta H, or enthalpy, minus T delta S, or our temperature and entropy of reaction. So realize that these are the same thing. We have delta G of reaction on the left, and we have delta G of reaction on the right. And so that means we should be able to set these two equal to one another, which obviously we can do. So in doing that, you would end up with something like this, that we have our left side of the expression, which is looking at delta G and K, or this negative RT natural log of K. And then that equals the Gibbs free energy expression we have on the right, which is the delta H of reaction minus T delta S. And so we can expand upon that a little bit more by moving our temperature around. If we simply divide over our temperature and our R value, we would end up with the natural log of our equilibrium constant is equal to a negative delta H of reaction over RT. And then that would be plus our temperature delta S of reaction also over RT. Notice that the negative sign in that division has changed that delta H reaction over RT to have the negative sign in front of it, as also changing that minus T delta S portion of the equation to a positive scenario. We have some cancellation here occurring. The temperature in this delta S portion of the equation, those are going to drop out. And we end up with something that looks like this. The natural log of our equilibrium constant is equal to the negative delta H of reaction over R. I'll write it a little bit differently. Still the same, but I'm going to pull that 1 over T out. I'll explain that in a second. And then we have our delta S of reaction over R. And so what we find here is that this is actually a linear fit, or a linear plot. That we have here y is equal to mx plus b. the natural log of our equilibrium constant is our y-axis. 1 over temperature is our x-axis. Our slope is the negative enthalpy of reaction over R. And then our y-intercept, or B, is the entropy of the reaction as well over R. So if we basically plot and, basically look to solve for slope, you get this equation. And this equation should look very familiar to us all now. We've seen it in a couple different renditions. We've seen it in terms of vapor pressure. We've seen it in terms of rate constants. And now we're seeing it in terms of equilibrium constants. Back in the first part of general chemistry, this was detailed as the Clausius-Clapeyron expression. All right, but that was talking about vapor pressure. And so in this case, we're just relating this now to our equilibrium constants. And so it's very similar in ideology as far as this relationship between now our equilibrium constant and our temperature. So this is the equation that we tend to use a lot, is this kind of delta idea, where here we have our delta y, here is our slope, and then we have delta x on the other side, right? Because delta y over delta x is the slope for a particular linear plot. So that's the expression. We've utilized this expression, obviously in different specifics as far as rate constants or vapor pressure, but mathematically it's really the same as far as natural logs, 1 over temperature. So let's do an example of this. So we basically have a reaction here. The following reaction we're going to be looking at is the decomposition of sodium bicarbonate, which undergoes an equilibrium decomposition to produce sodium carbonate, as well as carbon dioxide and water vapor. The delta H for this reaction is equal to 128.2 kilojoules per mole. So there's our reaction, and we have a number of values now as far as relating temperature to our equilibrium constant. And so we have 30 degrees Celsius, so we have a constant of 1.66 times 10 to negative fifth. We increase that to 50 degrees Celsius, we have a value of 3.90 times 10 to negative fourth. And at 70 degrees Celsius, we have a value of 6.27 times 10 to the negative third for our equilibrium constant. Basically, we want to determine the temperature at which the equilibrium constant is equal to 1.00. So that's our question. We have a reaction with the two sodium bicarbonates producing sodium carbonate, carbon dioxide, H2O. We have an enthalpy of that to be 128.2 kilojoules per mole. We have a number of temperature K relationships in our table here. And we want to basically determine that temperature at which the Kp is equal to 1. So if we go back to that table, we could put another value there, which is the 1.0 for our equilibrium constant. And what we're trying to figure out is that temperature at which we would reach that equilibrium constant of 1.0. So a couple telltale signs. Right here we have a temperature and equilibrium constant relationship. And guess what? There's only one equation that relates the two. Right, obviously that's what we were just talking about as far as that relationship in terms of the Clausius-Clapeyron sense. So we're basically looking at this expression. And so we just need to go up and, pick out, temperature and equilibrium constants. We're obviously looking at this value here because that's what we're interested in. We know our delta H that's already been given to us in terms of this delta H of reaction being equal to 128.2 kilojoules per mole. So we just need to figure out, the temperature relationships that we want to do. Remember, we also know what R is as well, right? R is just this 8.314 joules per mole Kelvin value. So in going up to the table, we really could pick, any of the trials if we want. I'm just going to pick trial there 4, I guess you could say, versus trial 2. But you could pick out you could pick out the 30, the 50, or the 70 in terms of temperature. And their respective equilibrium constants to relate it to the question at hand, which is what is the temperature at our equilibrium value of 1.00. So that means I'm saying a couple things in my pick that I'm also saying now that, okay, my KEQ1 is going to be equal to that 3.9 times 10 to the negative 4th. I'm also saying that my temperature 1 is going to be, that was 50 degrees Celsius, or 323 Kelvin. So that's what I've picked above for the trial 3 as far as those two values for my KEQ1, my KEQ2. Obviously, the other one is saying that what we're looking for is the second one where we have that value of 1.00, And what we're looking for is that actual temperature. So if we look above, we really have all the values here except for one. So if we start to plug them in, we go the natural log of K2 over K1, so I'm calling my K2 1.00, calling my K1 the 3.9 times 10 to the negative fourth. It doesn't matter as long as you're consistent with K1 T1, K2 T2. My personal preference is I always put the larger K in the numerator. That's just how I like to roll. But as long as you're consistent, you'll be fine. We then have our delta H. I'm going to convert it over to joules per mole. Again, that's important because of that R value in the denominator. So being careful again of units here with joules per mole, or if you want to go to kilojoules per mole, that would be fine too. You would just have to change your R value. Right, and then, and then that would be times our temperature, right? We're looking for that T2, and we know our T1 of 273 Kelvin. 323 Kelvin. So now we can, it's just be stepwise in the process. Students tend to try to move things all over the place, and I think that just ends up in confusion and miscalculation. So just go from one side to the next. Let's handle the left side of the equation. We take the natural log of that ratio. We get a value of 7.849. Right? If we break out the slope and look at that value, we would get a negative 15,418. Units for that would be technically in terms of Kelvin, so I'm just going to put that in alongside of it, right? The joules per mole is canceled out, and then in the denominator you have 1 over Kelvin, right? Which is the inverse of that, so that just means it's Kelvin. And then we have 1 over T2, which we're looking for, minus then 1 over 323, which is a value of 3.095 times 10 to the negative third, and that would be Kelvin to the minus 1 power. So those are our values. Again, being slow and stepwise, I handled the natural log on the left, I handled the slope on the right, and then I just handled that 1 over temperature value within the parentheses off to the far right. And so now what I want to do is just do some distribution, right? I want to bring over, basically, my 15,418. So I've just divided that over. And so that's going to then equal 1 over T2 minus that 3.095 times 10 to the negative third Kelvin to the minus 1. If I now add that to the other side, notice that I can add it to the other side because they're both of the same unit. They're both in Kelvin to the minus 1. That's equal to 2.586 times 10 to the negative third Kelvin to the minus 1. and that is equal to 1 over our temperature. And so now I can take the inverse of that, and I end up with my temperature equal to 386.7 Kelvin, or 113.7 degrees Celsius. So that is how we can actually relate temperature versus our equilibrium constant. I chose a harder version, which is solving for temperature. As an example here, realize that maybe you're solving for K as well, as far as maybe you're solving for an equilibrium constant K. So make sure you can do both of those algebraically, as far as, the inverse that I've shown here in getting to our T2 of 386.7. Again, this is where our value of K would now equal 1.0. But also realize you might have to get rid of a natural log if you're solving for K, so know how to use that e to the x algebraic manipulation. And that is the end of this second half of thermodynamics for second half of general chemistry. We're now moving on to redox chemistry in subsequent lectures. Hooray, hurrah!